So in this video, we're going to talk about how to solve problems using a tool called ICE tables. So in general, we will use ICE tables when systems are not at equilibrium and we need to solve for concentrations at equilibrium or the value of the equilibrium constant K. Not always true, but in general, this will allow us quantitatively to calculate concentrations of molecules at equilibrium if they're not initially at equilibrium. So far, all we've learned how to do is to predict the shifts. We're going to get quantitative in this video today. So, what we know is the equilibrium constant K is equal to Q when you're at equilibrium. And this is always, if you have a reaction of A plus B with, 2C, this is going to be the concentration of C squared over the concentration of B times A to the power of 1. Okay? We can only solve for K if these concentrations are at equilibrium. But what if we're not at equilibrium? What if when we plug in these values, we get a value for Q, and it's not equal to K? How can we calculate what these concentrations will be? Or, if we know the initial concentrations, how can we use those to calculate what K has to be? That's what we're going to do. So, I got two example problems that we're going to go over. Number one, consider the reaction below. H2 plus I2, hydrogen gas reacts with iodine gas to produce hydroiodic, HI. Bunch of information given. First big key when you're solving these problems is to read carefully. Read carefully. Take your time to think about the information that is given before you try to solve for anything in particular. So, for example, this says if the initial concentrations of H2 and I2 are blah, blah, blah. So far, we've been doing problems when the concentrations were at equilibrium. Initial is a key word that means not equilibrium. We're not at equilibrium right now with these concentrations. But we know for H2 it's 0.001 molar, and for I2 it's 0.002 molar. And the equilibrium concentration of HI is 0.0187 molar. So this is at equilibrium. So we have some weird things going on. We have compounds at equilibrium and some not. And the problem is asking for, in the end result, what is the equilibrium constant? K. What's K equal to? So, good rule of thumb, always write the expression, write the equilibrium expression. K is equal to HI squared over H2 times I2. So I'll probably need that at some point. What we're going to need to do now is we're going to construct something called an ICE table. An ICE table. So what I've done is I've rewritten the equation. This is what you're going to want to do when you solve these problems. And I'm going to draw a little table here. ICE are the three letters that we're going to use. I stands for initial. C stands for the change. And E stands for equilibrium. Basically what we're going to track here is what are the concentrations initially in the reaction at the beginning? How are they changing, meaning which way are they shifting and by how much? And then what are they going to be equal to when we're at equilibrium? So let's plug in the values that I'm given. I know that the initial concentration of H2 is 0.001 and I2 is 0.002. I'm not given an initial concentration of this, so I'm going to assume that it's 0 molar. If it's not given, assume it's 0. So I'm going to plug these in. 0.001 molar, 0.002 molar. I might even draw a little line to separate the products here. And this is 0. What else is given? The concentration at equilibrium of HI is 0.00187. So I'm going to plug that in down the bottom right here. Equilibrium concentration, 0.00187. Now I got to fill in the extra information. I'm trying to get K. So to get K, I need to know the concentrations at equilibrium. In order to plug numbers into here, I need to know what these values are at equilibrium. Since it's not at equilibrium initially, the reaction is going to shift. Which way is it going to shift? Well, we learned how to predict shifts using Q and K, but I can't solve for Q here because if I did, it's just going to give me 0 over 0.002 times 0.01, some number, which is 0. Since Q is less than K, this is going to shift to the right. Another way of thinking about it is since I have no molarity, I have no molecules of HI yet, the reaction has to shift to the right in order to make this compound form. So what I'm going to say is, since this is going to shift to the right, I'm going to put plus X. Because I don't know exactly how much concentration is going to be created. But another small point that a lot of people make mistakes on, since the coefficient is 2, it's going to form 2 times that concentration of whatever reacts. The coefficients for I2 and H2 are both 1. So whatever this gained, this compound must lose. The concentration of this is going to decrease. So we're going to write minus X. And they're both 1 because the mole ratio is 1. So what I can now plug for the equilibrium is I start with 0.001, and I'm going to lose some concentration. So I can write in minus X. And here I can write 0.002 minus X. So now I have the concentrations at equilibrium, except I don't know what X is. Except I do, because I know over here that 2X has to be equal to 0.00187. Because we started with 0, I gained 2X, and that became equal to this. So therefore, if I wanted to solve for X, I would just divide these by 2, and I would get a value of 0.000935. To get the concentrations of the other compounds at equilibrium, I just plug this value in for X here. So now I'm going to get 0.001 minus 0.00935 would give me 0.000065. I'm not doing scientific notation just for ease here. And this one is going to be 0.001065. So now to solve, think about what the question was asking for. I need to solve for K. What is the equilibrium constant? So now I have my equilibrium concentrations. I can plug in my values. So it's going to be the concentration of HI squared, which is 0.00187, over the concentrations of the reactants. And if I do the math there, I should get a final answer of 50.5. So the equilibrium constant K is equal to 50.5 for this reaction. Whew, that might seem like a lot. Main things to walk away from. Setting up an ice table. Initial change equilibrium. Coefficients tell you the value of X. It's not always going to be plus products. It might be. It could be plus on the reactant side, depending on the reaction. And then making sure to plug in values into the right spots. We'll do one more problem together, and then we'll get a ton of practice together in class. So, consider the reaction below. CoCl2 is in equilibrium with carbon monoxide, CO, and Cl2. I'm given K, okay? That might be helpful for me. I'm given the equilibrium constant. What information do they give me now? If the initial concentration, so that's, again, remember, that's not equilibrium, of CoCl2 is 1.5 molar, okay? So that's for CoCl2. What are the concentrations of each species at equilibrium? Remember, the word species is just another word for compound. So basically, we want to know what are the concentrations of this and this at equilibrium. So, rewrite the equation, set up an ice table. Okay? Initial change equilibrium. Let's think about the values that are given to me. I'm given the initial concentration of CoCl2 as 1.5. So I'm going to plug that in. CoCl2, initial concentration, 1.5. Draw a little line here to separate my reactants and products. Since I'm not given these, I know that initially they're 0. If they're not given, it's 0. Now I got to think about the change. What is my change going to be? Well, since I start with none of this stuff, that has to be formed. So this is going to increase plus x. And whatever that increases by, this is going to decrease. Again, each one of these has no number in front of it, or a 1 we could think of it, because the coefficients are 1 here. Boom. So just make that a little neater. This should be minus x, plus x, and plus x. So now, what will the concentrations be at equilibrium? Well, let's just rewrite all the numbers we have. It's going to be 1.5 minus x. This is 0 plus x, which is x. 0 plus x, which is x. Now, I want to write my equilibrium expression. Always a good start. K equals Cl2 to the power of 1 times Co to the power of 1 divided by CoCl2. I want to find out what x is, the equilibrium concentrations of these compounds. So what I'm going to do is I'm going to just take these three values and I'm going to plug them into my equation. So if I rewrite that down below, I'm going to get Cl2, the concentration of Cl2 is just x from here at equilibrium. The concentration of CO is x at equilibrium, and the concentration of CoCl2 is 1.5 minus x. What is that equal to? It's equal to K. Do I know K? I do. 2.2 times 10 to the negative 8th. So now I have one equation and I have one unknown. To make this a little bit easier for you, we can make an approximation. Whenever you have something in the denominator, and this is a key point to make a note of, when you have something minus x in the denominator, we're going to assume that the value of x is going to be very, very small. It's going to be very small compared to 1.5. So small that if we subtract it from 1.5, we're still basically going to have 1.5. So imagine, subtracting 1.5 minus 0.000001. You're going to get, 1.49999, which is basically 1.5. So we're going to make that approximation. It's so small, it's essentially 0. So if we rewrite this, we now have 2.2 times 10 to the negative 8th equals x times x squared over 1.5. So now, multiply 1.5 on both sides, and then solve for x. So we would have 3.3 times 10 to the negative 8th equals x squared. Got to square root both sides, and when you do that, you get a final answer of x equals 1.8 times 10 to the negative 4th. Boom. That is the concentration of Cl2 and the concentration of CO at equilibrium, which you would want to state explicitly. How could you check if your answer is right? Simple. Take this value, plug it back in here, and see if you get this answer. That's how you can check. A few key points, because this is overall a lot of new information on ice tables. Okay? Read carefully. Okay? You got to look for initial concentrations versus equilibrium, and what's asked and what's being asked. We want to know all that stuff before we even start writing anything down on paper. Watch coefficients. So what we mean by that, if the reaction is 2x to y and you're setting up your ice table, this needs to be, minus 2x, and this needs to be, plus y. The coefficients matter. Third thing, check your answer by plugging it back into your equilibrium expression. We'll get a lot of practice in class. These are a lot of different types of problems, but they all follow the same idea. We have a reaction that's not at equilibrium, and we're trying to solve something about it when it is at equilibrium.